Okay, so the next problem is the force acting on a bolt consists of two components, an axial pull of 12 kilonewton and a transverse shear force of 6 kilonewton. Okay. The bolt is made of this material FEE 310, which is not a brittle material, it's a ductile material. So SYT value is present here, SYT, yield strength in tension, which is 310 Newton per millimeter square, and the factor of safety is given as 2.5. Determine the diameter of the bolt using the maximum shear stress theory of failure. Okay, now alright, so let's start the problem. Here you see this problem is different than the problems we have solved previously. Okay, now we take a bolt. Okay, a bolt is under both tension and shear, they are telling. Okay, so this is the bolt. You have seen a bolt, right? So this is a bolt, we have some threads here. Okay, now they are telling that according to the question, an axial pull of 12 newton. What is the axis here? Axial pull. This is the axis, right? This is the axis of the bolt. So it is experiencing an axial pull. Obviously both sides you have to pull it, otherwise in one side there is nothing like a pulling. So 12 kilonewton, we are pulling the bolt. Okay, so an axial pull of 12 kilonewton. And transverse shear force. Transverse direction is always perpendicular to the axis, that is called the transverse direction. Transverse. Okay, so transverse direction is perpendicular to your axis, so it is being pulled in the transverse direction by another force, which will cause shearing. Actually not exactly here, somewhere here maybe, actually so that there is a failure like this. This will actually obviously cause a failure, but 6 and 6, if they are along the same line, okay, so they actually, yeah, it's up to you. Actually they may cause some failure, yes, but shear will take place when they are just not along one line. It'll be just like this. Okay, okay, anyway that doesn't matter for us. Actually they're just shear will take, they're saying that shear force of 6 kilonewton. I mean this thing 6 kilonewton is going to shear it. I mean the bolt is going to break, okay, here somewhere and like this. So this is for the force 6 kilonewton, which is parallel to the area, parallel. That's why this is a shear. Okay, so and another failure possible is when this is due to 12 kilonewton, it may break like this. Okay, this is the bolt. Okay, fine. So this is 12 kilonewton, 12, this is 12. So this is the area again, same area only, but this area is now perpendicular to the force. So this is your tensile failure. So in this problem, two type of failure is possible, tensile and shear, and you have to combine them, sigma t and tau. So you have to somehow combine. Now by looking at the previous problem, you may think like, okay, maximum your stress we will find out first and then we'll add them. No, in this case we cannot do that. Shear stresses cannot be added to, directly added to tensile stress or neither to bending stress. Okay, we have a we have to use the theories of failure for that. Okay, now have a look at this. Factor of safety is given to you 2.5. Determine the diameter of the bolt using the maximum shear stress theory of failure. So they have already given you which theory of failure to use. So maximum shear stress theory of failure you have to use. So given axial pull is okay, tensile force, shear force is this, so SYT is given, factor of safety is given. Okay, now to combine your tensile stress and shear stress, you have to look at, you have to go to your strength of material concept. Okay, when we have any set of stress, okay, to consider this one, okay, anything, when we apply sigma stress, sigma x, x direction, this is x direction, this is y direction, this is z direction. Okay, just consider only x and y direction sigma stresses are, these are ordinary stresses. Okay, or some these are not principal stresses, by the way. They have been they are applied stresses. We'll obtain principal stresses from them. Okay, these are applied, and shear stress is also applied like this in this tau xy. Okay, so perpendicular to x direction and parallel to y direction, xy means. Okay, this one it will be tau xy. Here also there will be another shear, this is tau yx, perpendicular to y axis and parallel to x axis. So these things you already know that you have solved in your strength of material problems like this, I think. So tau xy, tau yx. Okay, mathematically tau xy and tau yx, they are conjugate, they are actually equal to each other. Okay. So their magnitudes are equal, so tau x and tau xy, they are same. So here you see, just to find out, see, if we have a state of stress like this, sigma x, okay, sigma x in this direction, sigma y in this direction, sigma y in this direction. Okay, so to combine this, okay, tensile stress and shear stress, when we combine, we get maximum principal stress sigma 1, okay, we get minimum principal stress, and we get a maximum shear stress. So these things actually we obtain from strength of material, and we draw something that is called Morse circle. Okay, Morse circle. So I told you to look at these things once, and principal stresses, the I think the videos were given to you to watch, so I think you have watched them, you have understood them. Okay, so there is a from the formula also you can calculate all this, and from your Morse circle also we can calculate. So sigma 1 formula is sigma x plus sigma y by 2 plus root over sigma x minus sigma y by 2 square plus tau xy square. Okay, for sigma 2 this will be negative, this whole thing remains the same, and tau x is equal to this thing only. Okay, root over sigma x minus sigma y by 2 square plus tau xy square. Okay, this is the formula. Okay, now you see, alright, now look at this maximum shear stress theory. When you talk about that, then we have to consider this tau max. Okay, because tau max, according to maximum shear stress theory, the components will fail, okay, when your maximum shear stress for the specimen equals to maximum shear stress for the component. Okay, that is what we say according. So you have to look at tau max, so you have to use this formula in this case. Okay, so when you are asked to use maximum shear stress theory, use this formula. Now this has a what, tensile stress and shear stress term, and this is how we combine them together. Now this is for biaxial x and y axis. When we apply two tensile stresses in different directions, in x direction we apply one tensile stress, and in y direction also we apply some tensile stress. Okay, tensile or compressive, it's up to you, but it is normal to the area, and one shear stress is present. Okay, since tau xy and tau yx both are present, both are equal, so you can just take any one of them. Okay, so this is the complete state of stress. Now this is how we combine them. Now look at this. Okay, alright, so now, okay, so coming back to the problem. Okay, so now since we have to combine, now see in your problem, where is here, do we have, this is the component, one axis is this, let's say this is x axis or y axis, up to you. Okay, vertically is there, this is y axis, this is x axis. Do you have a stress, see 12 kilonewton will come, this will create some tensile stress. Okay, yes, so this will be sigma y, so some tensile stress, this is 12 by the area, failure area here. Okay, this is sigma y, right? So is there any other stress, tensile stress, this will cause shear, 6 kilonewton will cause shear only. Okay, and it's given to your problem. By the way, diagram is not given, so we do not know where the 6 kilonewton is being applied, so this will actually causing shear. Okay, so that is not a tensile stress, so sigma x is not there, right? Only one stress is there. Okay, if you consider this as x axis, no problem, you can just take the bolt horizontally also. What is the problem, right? So in that case, this is the bolt, right? So understand the concepts. This is 12, so this, in that case, sigma x is 12 by area, right? This is present. Sigma y direction, sigma y is not present, so in that case only one of your tensile stress is present, and shear stress is present. Shear stress will be 6 by area. Okay, 6 kilonewton by area, and this is how x y y x, whatever you want to write, because there is only one shear stress we have to consider. Okay, so now coming to your equation, see sigma x minus sigma y by 2 square plus tau xy whole square. This is how we combine. Now since one of them is 0, you can either take sigma x equal to 0 and sigma y is there, or you take sigma y is equal to 0, sigma x is there. So what will happen? This is tau max equal to root over, if you take sigma x is 0, this is minus of sigma y by 2 square, this is plus tau xy square, which is nothing but root over sigma y square by tau xy square, isn't it? Minus sign will come out this square, so it doesn't matter, this will be positive only. If you take sigma y is 0, sigma x is there, then this will be what? Root over sigma x by 2 square plus tau xy square, this is tau max, isn't it? So I mean either sigma y or sigma x, it is there. Okay, so only one stress sigma is present. Okay, so now see this sigma y, you can, or sigma x or sigma y, whatever is there, this is nothing but the tensile stress in your case. This is the bolt tensile stress. Okay, if suppose there is on bending stress is present instead of tensile stress, then you have to take bending stress here. Okay, sigma, I mean you just to get sigma, this term. So sigma, in this case bending stress and shear stresses are combined in this manner. So solve problems like that later. Okay, so now see tensile stresses are here. Okay, tensile stress, you'll put either your tensile stress is equal to either sigma x or sigma y. Okay, anything you like you can write, but only one is there. Okay, that means sigma t is what? This force by area. Okay, this area is perpendicular area, force is the perpendicular force, as a force is the force along the axis. Okay, and tau will be, tau xy will be force by area only, but this force is now the shear force divided by the area. Okay, then tau max is your maximum allowable stress, or the stress which you can allow according to your design. Okay, which should be less than your failure stress. Okay, SY, not SYT. For shear we learned that we have to take SSY is your, or yield in shear, it is S has to be the SSY is your failure criteria. Okay, and if it is, if ultimate is there, then SSU will be the failure criteria. Since it is a ductile material, so tau max should be equal to SSY, this is the failure stress, divided by factor of safety. Now in your problem we are given with SUYT only. Okay, yield strength tension. So how to get yield strength and shear? So that will be yield strength and shear is equal to 0.5 times SYT. Okay, that is half of your yield strength. So this is according to your maximum shear stress theory. If you can look at your maximum shear stress theory, look at this. Okay, have a look. SY equal to 0.5 of SYT. So this is what you have to use it. Okay, I told you this is important. So whenever it is written in your any numerical, you have to use that thing. Okay, all right. So now let's look at the problem and understand it. Now it is clear how to solve your problem. So according to maximum shear stress theory, this is the relation. See, tau max equal to SSY by Fs. So SSY equal to 0.5 by SYT. So you have found SSY. Okay, now look at this. We know for a set of stress, and this is actually the explanation I have written for you. You don't have to write down everything like that. You just have to write down maximum stress is given by like this, and there's only one stress, sigma, either sigma x or sigma y, that's up to you. Okay, that is actually depends upon, I mean only one stress is present, so and it depends upon your understanding. So for a particular problem, only one axial stress for this particular problem. Okay, for this particular problem, okay, we have only one axial stress and only one shear stress. So either sigma x or sigma y, it's up to you. So that is the tensile stress you take, because sigma. Okay, sigma t is equal to p by a. So force is given, axial pull is 12 kilonewton, so 12 into 10 to the power 3 newton, or divided by the area. So I told only sigma x or sigma y, not the both thing. Okay, both are not present, so that's why you have to take only one of them. So it doesn't matter if you take sigma x or sigma y. If you have taken sigma x, you make this as 0. So this is sigma t by 2. If you take this as 0, this as your tensile stress, this is minus sigma t by 2, which is nothing but sigma 2 by 2 only, because square is there. Okay, so this is your dimension of bolt is d, so the cross section bolt is circular, so this is pi d square by 4, which is your area, right? So this is your tensile stress. Similarly, shear stress, tau xy, yx, whatever you write, you can simply write tau, okay, which is your shear stress, okay, p by a. Now this this is shear force divided by the area. Shear force is given as 6 into 10 to the power 3 divided by the area is the same. Okay, area of the bolt is same here also. That's this area, in shear also the same area. Okay, so this diameter is d, small d. So this is pi d square by 4 is your cross sectional area. Okay. Now allowable stress is maximum shear stress is equal to this thing. See, I've already told you this is how we find. So Tom x equal to SSY by FS. So put SSY, FS is this one, factor of safety is this. So this is your maximum shear stress that we are going to allow, okay, which is much lesser than the failure stress, okay, failure strength, you can say 155. Here yield will take place, okay, due to shear, and we are not going up to that, we are just keeping it much below that, 62. And what dimension of what diameter of the bolt will keep it here?